Hello and welcome to the second video tutorial for the P2 chapter Sequences and Series. On the screen is a slightly different sort of starter. This starter is the question "Spot the mistake" from the previous video. Pause the video if you'd like to give this a few minutes thought, and then I'm going to go through and show you what I did wrong in the previous one. So in the previous video we had this question, a sequence has this formula where a and b are constants, the third term was 5, the eighth term was 20, find the values of a and b. And we put together some simultaneous equations using this information and the general formula. And then I found the common difference was 3 and the first term was 1, and I even went so far as to check that to make sure it was right. That's a 2. By writing out the sequence that this generates and showing that yes, indeed, 1, 2, 3, the third term is indeed 5, 4, 5, 6, 7, and the eighth term is 20. So my mistake was something that I keep telling my students, read the question, and I've gone and done the same mistake that some of my students do, and I haven't read the question properly. Because although all of this was correct, I haven't actually answered what it's asking me to do. Find the values of a and b, where a is the coefficient of n and b is the constant of the nth term. Which actually leads on to a second mistake in that I shouldn't really have used a for the first term, although that's normal, and your examiner would probably forgive you for mixing these a's up. But because a here is the coefficient of n, I shouldn't use a to mean something different here. So if I correct myself, let me call that c instead. Not the best question because it's common to use a for the first term, and they haven't done. They've used a for something else, which is a little bit weird. But it's allowed, and it might happen in an exam. So if I use c to represent the first term, then the question actually wants me to find a and b. To do that, I need to find the nth term. So let me finish this question off for you. U of n is equal to, well, I was going to write a, but I've got to put c, my first term c, plus n minus 1d. This is our general formula. And usually I write a, but I've put c again because they've used a for something else here in the question. So the first term is minus 1 plus n minus 1 times d, the common difference, which is 3. And if you expand that out, or if you use the alternative method, you end up with a minus. I seem to have done that wrong. I need a little plus in there, don't I? You end up with a 3n minus 4. That looks right. And then you can check this again with the sequence that it generates. If you put a 1 in here, 3 minus 4 is minus 1. If you put a 10 in here, 30 minus 4 would be 26, which would be the next one here. So that's correct. So my actual answer here, after all of that, the a from the question, not the first term of the sequence, but from the question, a is 3, which is actually our d when we were doing the working out. And the b in the question is a minus 4. So apologies for doing something I keep telling my students not to do. I didn't read the question properly. So that finishes that from the previous video. There was also another minor typo in the previous video. If you saw a place where there was no opening bracket, well done. It didn't make much difference, but that error was in there as well. Hopefully fewer errors in this video, which we're going to do geometric sequences and series. Now a lot of the slides are going to look very similar to the previous one because there are a lot of parallels between arithmetic sequences and geometric sequences. So let's get straight in there. Quick reminder, sequence is a string of numbers that follow a set pattern. A geometric sequence has a common ratio. Now this is very similar to the common difference, but it's subtly different. The common difference of an arithmetic sequence is adding or subtracting the same number each time. Common ratio is multiplying or dividing the same number each time. Although we don't really use dividing, we use multiply by a fraction if it's dividing. So we've got a common ratio. And same as with arithmetic sequences, geometric sequences are also known as geometric progressions. So you need to know that a geometric progression is just the same thing as a geometric sequence. So here are some examples. Quickly go through the three examples and put down the common ratio and their first term. Now the first term is still represented with an a, as with arithmetic sequences. The first term here is 2. And for the common ratio, we use the letter r. So the common ratio here, if you look at the numbers from 2 to 4, is multiply by 2, multiply by 2, multiply by 2. So we've got a 2. For the second one, the first term is a half. And from one to the next, we're dividing by 3, divide by 3, divide by 3. But as I said earlier, we don't really do a divide by, we do a multiply by 1 over 3. So the common ratio is a third. Another way to think of this ratio is by taking any term in the sequence and dividing by the one before it. So 1/6 divided by 1/2 would give you 1/3. And the last one, just to show that you can also have a negative ratio, a is 5 here, and the common ratio here is a -2. So if all the terms are positive, or if all the terms are negative, then your common ratio is a positive number, because it's not changing the sign each time you multiply. But if you get alternate or oscillating between positive and negative, then your common ratio is a negative number. So watch out for that. As with arithmetic sequences, geometric sequences have an nth term formula. And for a geometric sequence, you're multiplying by the ratio each time. So you start with your first term, a, and then you multiply by r to get the second term. You multiply by r again to get the third term. And as you multiply by r each time, you end up with a power of n-1. So for the first term it's not there because you don't need the common ratio for the first term, and for each subsequent term you've got an extra r multiplying. And you just need to be able to apply this. So 3 to 6 to 12 to 24, a is obviously 3. The common ratio here is a 2, so the nth term is 3 times 2 to the power of n-1. And personally, I do the nth terms first because although you could do the 10th term by just following the pattern for 10 numbers, I find it easier to use the nth term now that I found it to then put in n equals 10. Do this in purple. So the 10th term is 3 times 2 to the power of 10-1, which is 9. Bang that on your calculator. 3 times 2 to the power of 9 is 1,536. There might be times that you're allowed to leave that in index form, but if the number isn't too ridiculously big, usually you'll be asked to put it in just a normal format. Second example, we've got a is equal to 40. Here r is equal to a negative, and it's getting smaller by 2, so it's -1/2. That makes my nth term 40 times, now be careful to put your negative r in a bracket here, because that negative is part of the r, so that also needs to be raised to the power of n-1. So put brackets around that if it's a negative. And then once I've got that, my 10th term, I'll just put n equals 10 in there. 40 times -1/2 to the power of 10-1 is 9. And again, put that on your calculator. And this time we get -5/64. Okay, Here are some slightly more involved examples. The second term of a geometric sequence is 4, and the fourth term is 8. Given that the common ratio is positive, find the exact value of the 11th term. Okay, so I'm going to just put up here the general nth term of a geometric sequence, just to remind me. So the second term is 4, so u of 2, which is a times r to the power of 2 minus 1, which is just 1, must equal 4. And they also tell us that the fourth term, which is a times r to the 4 minus 1, which is 3, must equal 8. So we've got two bits of information, and using this information I can divide one by the other. So I can divide this by this to get rid of the a's. So 8r cubed divided by 8r must be the same as 8 divided by 4. And I get r squared must equal 2. So r is equal to plus or minus the square root of 2. However, they've also said, given that the common ratio is positive, so I can go one step further and say that r is specifically the square root of 2. Then find the exact value of the 11th term. Well, if I know r is equal to the square root of 2, then I can use this bit of information to find a. So a must equal 4 divided by the square root of 2, which is 2 root 2. Oh, I should do that on my calculator just in case I do a silly mistake, because sometimes I do, as you know. 2 root 2, yep. So I know a, I know r, and I want the 11th term. u11 is equal to a times r to 11 minus 1 is 10. And I know what these are now, so 2 times the square root of 2 times r, which is also the square root of 2 to the power of 10. So 2 root 2 times the square root of 2 to the power of 10, and they want it in an exact form. So I've got 64 times the square root of 2. I don't convert that into a decimal because of this wording in the question, the exact value. So I'll leave that in third form. Next example. The numbers 3x and x plus 6 form the first three terms of a geometric sequence with all positive terms. That's important because it tells us our common ratio is positive, not negative. Find the possible values of x and the 10th term of the sequence. I suspect that is a slight typo there because they've told us they're all positive, so we're only going to have one possible value of x. But we'll see just if that's correct if we go through. So numbers 3x and x plus 6 form the first three terms. So a, straight off the bat, is 3. A times r is x. And a times r squared is x plus 6. These are the first three terms of any geometric sequence. And this specific one, 3x, x plus 6. Which tells us, using the first two, if a is 3, then r, the ratio, must be x divided by 3. Is that helpful? Well, yes. If we now put this and this into here, we can eliminate a and r from this equation and get an equation just in x. So let's go ahead and do that. So that tells us that 3 times r squared, which is x over 3, is equal to x plus 6. One of those 3's cancels out, so I get x squared over 3 is equal to x plus 6. Multiply everything by 3 and rearrange. I get x squared minus 3x minus 18 is equal to 0. I feel like I should be able to factorize that rather than use my calculator here. What have we got? A 6 and a 3. Minus 6 plus 3. That looks about right. So x is equal to 6, or x is equal to -3. Now I suspect that's what they mean when they say find the possible values of x, is if you stop there. But they do tell us that all terms are positive, so r must be positive, which, given the relationship here, means x must also be positive. And that's because r must be positive from the question. So if we used x is equal to -3, that would give us r is equal to -1, which contradicts what they told us. So although I guess from this point you could say there are two possible values, really there's only one that gives us the correct r value. And now they want us to find the 10th term of the sequence, so we find that by using a is 3, r is 2, and using our formula. So u10 is equal to, remembering un is equal to r to the n minus 1, I'm using this formula. u10 is a3 times r, which is 2 to the power of 10 minus 1 is 9, and I think we had that earlier. Yes, 1536. There we go. Final example on this. What is the first term in the geometric progression 3, 6, 12, 24 to exceed 1 million? As we had in the previous video, this is going to be an inequality. So we've got u of n is equal to ar to the n minus 1, and we know a is equal to 3 and r is equal to 2. Having low numbers here is quite common. That's why we're having so many ratios of 2, because if you have an r value that's too high, you can end up with a question that's just got ridiculously big numbers, and exam questions try not to be too ridiculous with their numbers. So our nth term here is 3 times 2 to the n minus 1. So what is the first term to exceed 1 million? So when is this thing bigger than 1 million? That's the question. So we can just divide by 3. I'm going to leave it as a fraction. And then, well, I guess we could do sneaky log here, couldn't we? Remember your log rules. I'm going to use natural log. And then just check if you're going to divide by the log of 2, unless it's already in your mind as to what that is, just double check that that is not a negative value. Because remember, if you divide by a negative value with an inequality, you've got to switch that sign. But the log of 2 gives us a positive value, so I don't need to switch the sign. So the log of 1 million over 3 divided by the log of 2 gives me the answer 18.34 ... So that is equal to n minus 1 because I've divided by the log of 2 there. So n must be greater than 19.34 ... And if we want the first one to exceed this, we need the next one up. N is greater than this, so n must equal 20. And if you've got time in an exam, check that out by putting n equals 20 back in and finding that that is bigger than 1 million. And if you've got lots of time, put n equals 19 to find that that isn't quite bigger than 1 million. Or actually, with a geometric progression, it might be quite a lot less than 1 million. It'll be about 500,000, a little bit bigger than that. Okay, as with arithmetic, I'm going to go through this slide very quickly, because as with arithmetic sequences and series, geometric sequences and series, it's the same idea. A series is just taking your sequence and adding the terms. And there's a formula for the geometric series sum of the first n terms, and the formula is this. I'm not going to talk about it on this slide because you might be asked to prove this, so I'm going to go through the proof on the next slide. as with the arithmetic proof, what we do here, we start with the general terms written out. However, with the arithmetic proof, what we did was we switched them around, making the last term the first term, and the first term the last term, and then adding them together. We're not going to do that. It's a slightly different approach. What we do here is we multiply everything by the common ratio r. And this will make sense in a minute as to why we do this. So a times r is ar times r is ar squared, and of course they're all still added together. Ar squared becomes ar cubed, ar power 4, ar to the n minus 2 times r becomes ar to the n minus 1, and ar to the n minus 1 times r becomes ar to the n. Now we can subtract these two. And that gives us, on the left, r times s of n, the sum, minus the sum. And what you see here, hopefully, is that you get ar minus ar squared minus ar squared, ar cubed minus ar cubed, and so on, all through the middle, all the way up to ar to the n minus 1 minus ar to the n minus 1. So all of these are cancelled with the terms in the dot 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 bit here. And all you have left is ar to the n minus a. And then we can do a little bit of factorizing here. We've got s of n r minus 1 is equal to a r to the n minus 1, and divide through to get our formula. And there we have it. Now there is an alternative form to this formula, because when we did this bit here, instead of subtracting the green equation from the blue equation, we could have subtracted the blue equation from the green equation and had something very similar. We would have ended up, if you'd gone through it all, with 1 minus r to the n instead of r to the n minus 1, and 1 minus r instead of r minus 1. And hopefully you can see, if you factorize out the negatives here and here, then you switch around the terms and the negatives that you factorize will cancel. So it's equivalent expression. Why these two are often put together, however, is because this one can be useful when r is bigger than 1 to avoid pesky negatives, and this one can be easier when r is less than 1 to avoid pesky negatives. So you do see these two being used on different occasions, and the only reason for that is to choose the one that will avoid giving you negatives in your working out, because negatives are sometimes a bit harder to make sure that you've done correctly. But they are equivalent, and you can see both in booklets, in textbooks is what I mean, and you can use both, whichever one you prefer. So using that, and put it up here, Sn is equal to a r to the n minus 1 over r minus 1. Using that to find the sum of the first 10 terms of the geometric series 2 plus 6 plus 18 plus 54. Okay, first of all, as with the arithmetic, get your information. A is a 2, r is, in this case, a 3, and we want 10 terms, so n is a 10. Then we've got everything we need, bang it in the formula. We've got a 2 times 3 to the power of 10 minus 1 over 3 minus 1. And this is obviously going to be a very big number, because if you think about what we're doing here, the geometric series gets very big very quickly, and we're adding all of the terms together. So I'm expecting quite a large number, and it is 59,048. As long as I haven't made a calculator error. Next one, find the sum of the geometric series this. This one's a little bit different, but I'm going to approach it in a very similar way. A is equal to 1024, r is equal to, because they're alternating negative positives, it's negative, and it's getting 2 times smaller each time, negative a half. Now the difference here is that n is not entirely easy to see. However, because of the sequence, you can just figure this out by putting the numbers in. So going from 1 to 1024, if I multiply by 2, and then I get 4, that's 3, 4, 5, 6, 7, 8, 9, 10, 11. And what I've done there is I've just put on my calculator 1 times 2, and then answer times 2, until I get to 1024, and I counted how many times I had to press the equals button. So because this is a very limited sequence, it doesn't go on forever, we can see the first bit, we can see the last bit, it's quite easy to work out the number of terms in between just by going for it and figuring out what they are. So once I know that, I just put it in the formula as before, 1024, r minus a half, remember to put that in brackets when you do power of 11, minus 1. And all of that is going to be minus a half, minus 1 on the bottom, divided by minus 3 over 2. So I've got minus 1 over 2 to the power of 11. Then I need to subtract 1 off of that, multiply it by 1024, and divide that by minus a half, minus 1. And I get the answer 683. Now you could argue with this when I said about how to get the number of terms just by sort of basically figuring out what all the terms are. It could also be that you don't want to use this formula at all, because if you know what these numbers are, you can see the pattern, you could just stick it all on a calculator. And if you just put this in, 1024 minus 512 plus 256 minus 128 plus 64 and so on, as long as you got your plus and your negative correct all the way through, that you might argue is a slightly easier way to get this answer. And that's fine. If it doesn't say use the formula, that is absolutely fine. Just make sure you're doing what the question asks. Final one, find the least value of n such that the sum of 1 plus 2 plus 4 plus 8 blah 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 to n terms exceeds 2 million. Okay, it's already become pretty obvious on this, but yes, just keep in mind you might need logs to solve some geometric series problems, and we have already used logs on a previous question. So I'm going to need logs again here. Get rid of that to give me enough room to write this answer. So again, let's just write down the information we've got. A is a 1, r is a 2. The sum, not the first term like we had before, but the sum needs to exceed 2 million. So S of n is equal to a 1 times 2 to the n minus 1. Just putting a and r into the formula at the top. And r is 2 minus 1. Simplify this a little bit. 2 minus 1 is 1. Obviously, all those 1s outside the bracket just become the bracket itself. There we go. So this sum, 2 to the n minus 1, they want it to exceed 2 million. So 2 to the n needs to exceed 2 million and 1. So if I do, I'm going to use natural logs again. The natural log of 2 we did before is a positive number, so when I divide by that I don't need to switch the sign. So the natural log of, let me get this right, 2 million and 1 divided by the natural log of 2 gives me the answer 20.93. So n must be bigger than this, so n must equal 21. And as I said before, as I've said every time, if you've got time in the exam, you can just put that number back into the sum formula and make sure that it does give you a number bigger than 2 million. And if you've got lots of time, put the number before that, n is equal to 20, and make sure that it gives you a number that is not bigger than 2 million. And then you can be sure that you've got it right. And that is the end of the arithmetic and geometric series and sequences section. In the next one, we'll look at taking this a little bit further in the sum to infinity. Maybe I'll see you in that video.